And there we go. So welcome to the second session today. We had a pretty good group also before lunch. So going through this exact same material that we're going to go through today. Just kind of an FYI, these courses is courses that we've been rolling every single year. Right now we have 5 different courses that we're offering, and they're the intent here versus, for a lot of you guys, we've been having in-person courses where we kind of do kind of like a crash course for the software. Well, these courses are more intended if you want to do kind of like a deep dive into one particular part of the software. So we have the PDT course in February. There we only spent 4 hours focusing on every single part of the PDT piece of the software, both the theory and how to use it. Same thing we did with the bottom of pressure course, and then there was an RTA course, and this is the flow material balance course, and then next month Graham is going to teach the nodal analysis course, so that'll be fun. This course, even though we have 4 hours, it's probably going to be around 3 hours. That's because it's a little bit more straight and to the point. It's also, when it comes to actually knowing what to do, there's only so much we can cover here. So probably we'll expect to be done here probably around 3, maybe 3:30, or probably 3:30 Houston time, something like that. We'll also take some good breaks in between. If there should be any questions, feel free to send those questions in the chat or just unmute at any point in time. What hopefully you'll appreciate is that we're going to cover the theory. We're going to go through some case studies with real data, a couple of case studies from the Eagle Ford, a couple from the Permian. And then the last thing is that we're going to go ahead and do a lot of these things together in the software. So that's kind of the 3 different things that we'll touch upon today. If you don't see my screen, shout out, because I'm at least sharing the screen. I hope so, at least. So the course is, as I mentioned, recorded. So that will be uploaded on our YouTube channel later, and these recordings will be available, forever for all of you guys. So if you had to jump out, if you want to rewatch it later, etc., you can do that. Also, if you took this course last year, for instance, I don't think there's any. We had this similar course last year. There is. We try to always renew the content, make it more up to date, more relevant. So this is a newly updated course, and we update these courses every single year. When it comes to the software I'm going to use today, it's of course Whitson Plus, but it's not your office domain, if you like. So all you guys are working for operators that have access to the software, and you have your own domain, but today you're going to use the courses at Whitson.com domain right there. And if you have any issues, don't contact Mo. He's actually in Saudi Arabia teaching a course for Aramco today and tomorrow, but send an email to support@Whitson.com. So I'll just mention that if you're not able to log in, then contact support@Whitson. And I'll just write it here that the username, that's your email. We also mentioned that in the email we sent out yesterday. The password is Whitson FMB 2023 star. And again, if that doesn't work for you for whatever reason, send an email to support and we'll help you with that, hopefully ASAP. Perfect. So that's getting access to the software, and it seemed like someone had been requesting support already, so that works at least. So Jason's going to help whoever sent the message now. So that's going to be awesome. Perfect. So that's the first piece. So just to make sure that we can do this together, just open your browser, go to courses.whitson.com. I'll be logged in already because I did this before the break, but if you go here, make sure that you click here, fill in your username, which is the email, and then your password right here. and then you click continue here. Once you're done with that, you can just do this. Okay, perfect. Goodie. Once you've logged in, let's just make sure that you're in this course called the FMB course. And in the FMB course, you just make a project. And we'll go ahead and do that a little bit later. Perfect. So very quickly on what we're going to talk about today, we're going to talk about the FMB method, and as I mentioned, it's a part of the series of courses that will be available when in recording later. We're also going to run those courses also next year, so in case some of your colleagues would not be able to access it, let us know. If you need a certification or like a course certificate for petroleum engineering points, etc., just send us an email after that. But what we'll cover today is the basics of Multiphase FMB, primarily structure and functionality related to that. And as I mentioned, it's a primary and only focus on the full Multiphase FMB workflow with the Multiphase FMB and recovery factor analysis. So we'll assume here that the inputs are correct, that the PVT bottom-hole pressures, when we do exercises, that's what we're going to assume. But we'll talk a little bit about that as well. A nice thing is that we can also, we'll talk about that for like dry gas wells. We of course also have the auger well material balance in the software. You can actually use the Multiphase FMB for dry gases as well. So that's, and all the concepts and theory and stuff is very, very similar. So we'll just try to kill two birds with one stone on that front. We also believe that it's important to be practical, so we're going to go ahead and use a lot of these things very fast, and we're also going to show real data and real case studies. And there's also a lot of the slides that you'll see be repeated, and they're going to be repeated on purpose. So if you've never done a flowing material balance exercise before, that is different from RTA. It's kind of a subcategory of RTA, I would say, or like modern RTA, the way we think about it. But there's no, you don't need like to actually know what the height is to do this type of work of the reservoir. You don't need to know the porosity of the rock to do this type of work. And you don't quantify an LFP or like an A root K parameter when you do this type of work. So what is a flow material balance exercise used for? Well, it's used for trying to estimate the contacted pore volume. A well is draining from a reservoir. And in a conventional sense and in an unconventional sense, the objectives are the same and the purposes of the objective is also the same. So in a conventional reservoir, you have all these complicated petrophysical models. You go ahead and map your in-place volumes. You drill these wells there. Use this method to see, okay, of all the resource in place, how much am I able to contact? In that contacted pore volume, your recovery factors will be, fairly large. But in the parts that you don't contact, in a conventional sense, maybe that's because of fault systems and that kind of stuff. But in tight unconventionals, it might just be due to that your completion isn't effective enough, or that you're still infinite acting. But no matter where you do a flow material balance exercise, it's just an accounting exercise that uses a very simple graphical technique. In the software, in our software, in Cotero's internal engineering software, and EOG's internal engineering software, the flow material balance goes up and to the right. In some other tools, it goes down, or I guess down and to the right. The difference is that the only difference, in a nutshell, is that whatever is plotted here on the y-axis is flipped. The reason why it's flipped is when you plot the inverse, these late time point or the late points right here, they'll be stretched out graphically, so it's easier to interpret. Well, what happens very often if you don't do that, you get this cluster. If you do the inverse, there'll be this cluster of data points right here. That said, we'll most likely just include a little toggle, so you can probably plot both of them in the software here at some point in the next few months. But I just wanted to mention that for those of you who probably have that question as we go through the material here. What is lovely with the flow material balance, as you'll see as well when we're going to do the exercises, they're going to be like this. They're going to be fast. And that goes back to the beauty that, you know, a flow material balance exercise is the whole essence of it is this quote right here that I love. It's better to be roughly right than precisely wrong. It only needs PVT properties, form bottom wall pressures, and production data. That's it. Nothing else more complicated. So it's one of the analysis that is like physically constraining, that needs the least amount of input data compared to like a numerical model or compared to like a you know, analytical or numerical RTA exercise or whatever. So that's the beautiful thing about it. And if you look at it in a little bit broader context, it's kind of after you've gotten PVT and bottom wall pressures, you can do this exercise, and then, you know, downstream from that, that's typically when we do RTA and simulation exercises. So it's kind of this step right here. That's what we're going to focus on today, and we're actually not going to talk about much of the other things. There's dedicated courses for that. To really understand and to appreciate these flow material balance techniques, you need to have an extremely strong, I think, mental framework when it comes to looking at wells and well performance. The things I always repeat there, and I'm going to repeat it till I die probably, and I show it as many times as I can, is the two next slides. And that's because if you don't have the two next slides crystal clear for you before you start to do any type of work on a well, or before you go ahead and try to analyze a bunch of wells, your world will be extremely messy and complicated. So that's why we always go and spend a lot of time on it. So when it comes to the flow regimes, there's 3 different flow regimes that we typically look at for tight unconventionals that we bucket wells into. Those 3 different buckets is infinite acting flow. That ends as a pressure transient had reached one of the reservoir boundaries. Then boundary dominated flow, that starts when the wellbore pressure response is affected by all the reservoir boundaries. So these 2 are 2 complete extremes. Boundary dominated flow is what we call tank-like depletion or pseudo-steady state. It's what we learned about in university. All conventional stuff that we learned about, boundary dominated flow. And then in between there, we have this flow regime that we call transitional flow. So we might have seen one of the reservoir boundaries, but we haven't seen all of the reservoir boundaries. Okay, so you can think about this as if you're asked to find out with your eyesight how big a room is, when you're infinite acting, that's where you basically you haven't been able to or been allowed even to enter the room, so you can't see anything within the room. So it's only upside. It can be infinitely big. You don't know. You don't have a clue. And then once you're in transitional flow, that's when you've been allowed to enter the room and you've seen a couple of the walls. You might see the wall in front of you and the 2 ones on the side. And you can at least estimate, you know, maybe it's 2 meters in front of you and 1 meter on each side, okay? And you know the height of the ceiling and stuff, so you can calculate the volume there. So you at least know the minimum amount of how big the room is, but you still don't know where the wall behind you is. So when you've turned around then and you see, okay, that wall behind me is 4 meters behind me, that's when you're in quote-unquote boundary dominated flow, and you have all the information you need to be able to say how big the room is. And it's a similar way that you can think about this to some degree. And we'll get back to that analogy a little bit later. The second thing to just remember is when, you know, since I said this is a subgroup of RTA, and a lot of you guys I talk RTA with almost at least weekly, what is important to emphasize is that an RTA exercise gives you 2 outputs, A root K, one of them, and contacted pore volume is the second. The item to the left, you can only quantify if you're in true infinite acting linear flow, and the item to the right is something you can only quantify if you're in full boundary dominated flow. So what the flow material balance technique and like a RTA exercise has in common is that they both try to quantify this term to the right here, the contacted oil or gas in place. And if you're in full boundary dominated flow, there should be no reason for these 2 methods to yield a different result. If there is a different result, there's something inconsistent with your models. The problem is many times with these wells, we might be infinite acting in transitional for a very, very long time. So then the flow material balance technique will give you a lower estimate, and we'll talk about that in a sec. But that's the common goal of both of them. And this common goal, estimating this contacted pore volume, that is very important to understand, because it's not the petrophysically mapped in place volume. So if all of us learned maybe that in well logging or whatever that course was in university, when we wanted to calculate in place volumes and that kind of stuff. When we did that, we were given a block of rock. We know the height of it, the porosity, the saturation, and maybe some PVT properties, and we use that to say, okay, this is the whole block of rock, and this is how much oil in place or gas in place it is in that block of rock. But in reality, what happens is that we have the block of rock there, and then we're putting some wells in there that we add in a completion to, and we're just able to access a subsection of that block of rock throughout the lifetime of the well. And that subsection, of that subpart, is what we call the contacted pore volume, and it's a thing it's a thing in a conventional sense, and it's a thing in an unconventional sense as well. This pore volume, I emphasize to you guys, we call it the contacted pore volume. Some people call it the stimulated rock volume. Some people call it I guess a combination of all of this. Some people call it the drained rock volume. Like, I don't care what you call it, just that you remember that what you resolve in an FMB method and an RTA method is fundamentally different than what the petrophysicist gives you. The petrophysicist gives you the whole tank. Well, you're basically saying, okay, I put 8 different wellbores in the tank. How much is each of those individual wellbores able to contact of what's already there in place? And we did a survey last year with all of you. Maybe some of you guys remember. And the haircut is huge. And there was a bunch of case studies that was shown in the knowledge sharing sessions and stuff. Very seldom that you can get over 40%. That the blue region is more than 40% of the gray. Most of the times we saw it was between 20 to 40%. So that big haircut, that's why you get, when people talk about recovery factors of 4 to 10%, that's why you get down to that range. Because there's a bunch of the rock that will never be stimulated because the fractures aren't, cluster efficiency might not be 100%, fracture height might not be 100%, constant and effective. The fractal lengths will be different, etc., etc. So just keep that in mind. And in the blue region, we can get recovery factors of 20, 30% for oil. But if you reach a certain abandonment pressure. But in the gray part, depending on the perm range, it can be everything from some to almost or basically zero. How do we quantify this contacted pore volume? So the main exercise with the flow material balance, the only thing we really care about, the size of the tank that this well is draining. How do we quantify it? We can quantify it with a, it could just be up, the actual reservoir pore volume. But more commonly, we use the oil in place for oils and gas in place for gas. It really doesn't matter what you use here. You can use all of these interchangeably. The only difference between them is the pore volume and PVT properties. So it really doesn't matter. In practice, probably it depends a little bit. If you want to look at pore volumes consistently for a whole play where the fluid properties are changing, maybe you would like to quantify the pore volume, because that will of course be a more fluid agnostic way of looking at it. But except from that, pick your poison. It's the same thing. The last thing that I'd like to emphasize is related to boundaries. So a lot of the simple models we use in Titan conventionals are these symmetrical element models, or these single fracture models that we add up. All these models have only 2 boundaries. It's one boundary at the end of the model here, and there's no volume beyond the frac tip or frac height. So there's only one direction of flow. That's from the matrix into the fracture. That's what we call a one-dimensional model. How many flow regimes do you have? Well, you only have 2 flow regimes in this case, infinite acting and boundary dominant. If we add these next to each other, it's still one boundary because we see the boundary at the same time. still a one-dimensional model because it's just a series of one-dimensional models, and it only has two boundaries. And that means that it only has one boundary, so that means that it only has two flow regimes. This guy, however, has two boundaries. Now we added some volume beyond the frac tip, and this is what we call a two-dimensional model. So there's no volume beyond the frac height, but there's some volume beyond the frac tip, and we're getting contribution because the perm is high enough to then have fluids that's flowing into the kind of the stimulated rock volume. Okay, so now we have two boundaries. It's a two-dimensional flow. And then immediately we'll have three flow regimes. Well, infinite acting flow initially, and then once you're in boundary dominated flow with the boundary over here at the side, you're entering transitional flow, and then it will be a humongous long wait until you're actually in full boundary dominated flow out here. That will take a really, really, really long time. Awesome. So when you have three different flow regimes, that's potentially that you can stack up over time. I know we've talked a lot about this, but it's important for the audience here to just know what world we live in. You can have only 7 different sequences of flow regimes with time. The first is that you're only infinite acting for the whole observed history. Then the B factor is 2 on your DCA if the bottom pressure is constant, yada yada. The line is straight in the square root time plot. Or you can have infinite acting flow followed by transitional flow for the observed history. You can see infinite acting flow followed by transitional flow, and then finally boundary dominated flow. You can go from infinite acting to boundary dominated flow, transitional flow for the whole history, transitional flow followed by boundary dominated flow, or boundary dominated flow for the whole history. And I understand this is a lot of information, but these are the sequences that we can expose a well to. And if I've did my combinations right here, it should be 7, but let me know if you disagree. Anyways, so we'll continue now, but the reason why we emphasize flow regimes hopefully will be a little bit clearer when we're going to go ahead and talk about the flow material balance techniques themselves. So that's why we start with the crash course, and then we're going to do, after a while, we're going to do like a break and stuff, and then we're going to revisit a little bit of this later. So the multi-phase flow material balance is trying to solve a very fundamental problem, and that's that all the multi-phase techniques that we have, they require rel perms as an input. But in reality, we don't have relative permeabilities available to us for a lot of these rocks. So a few years ago, when Leslie Thompson and Barry Ruddick, they were at Cimarex, they said they developed a new multi-phase FMB method. Does not require rel perms, does not care about geometry, and outputs the contacted pore volume with a straight line technique. When you hear this for the first time, you seriously think this is way too good to be true. And we were no exception of that. So honestly, when Curtis and I heard it, we were like, okay, this is probably BS, but let's go and check it. And when we checked it, we ran into this problem that single thing we did with the simulation models, complex models, simple models, pressure-dependent permeability, low fracture conductivity, anything I threw on this guy came out with the right result every single time. So it captures the pore volume in terms of if you check it towards cases where you know what the pore volume is, and you can change the rel perms and all these things, all kinds of fluids. So we know the methodology works now, and it's been proven, tons of times. It's been used all over North America now in day-to-day operations. It does not require rel perms. It outputs the contacted pore volume. Does not care about geometry, but like any of these flow material balance techniques, whether it's Blassingame, Agarwal, disk material balance, etc., it assumes boundary dominated flow. Okay, so all of these flow material balance techniques, and so for them to give you the right answer, they will always assume boundary dominated flow. And if you're not in boundary dominated flow, this will always be a lower estimate of your contacted pore volume. And a lot of people is like, yeah, but why can you use them for unconventionals? Well, then they don't realize that there's a lot of good information in that. First of all, if you have a lower estimate of your contacted pore volume, you can very quickly compare. And I do this all the time. It's actually a very, very good check. You do your DC. Your first thing should be to just run your DCA. Use an autofit or whatever. I don't care what it is. just whatever, it will be okay. And then for an oil, for instance, you will run the flow material balance, and if you, for instance, are infinite acting, you'll get a very low contacted oil in place. And that, even before I've looked at any of the square root of time plots, any of the numerical RTA stuff, the only thing I've done is to run a straight line through that data. I can already tell you that I'm extremely confident that this well is still infinite acting, or at least transitional. Okay, so you can use it in that way as well. And hopefully throughout this course, I'll teach you 3 other checks when it comes to the multiphase FMB that it can give you of more physical things, even if it's still infinite acting. So we'll get there a little bit later. So it's actively used to bound RTA work if you're still infinite acting or transitional. Okay, so the reason why it makes sense, right, that multiphase flow material balance, or flow material balance in general, whoever designed this material balance method, whatever material balance method you use, the reason why it makes sense that it assumes boundary dominated flow is because the objective of the exercise is to find the size of the tank. But how can you know the size of the tank if you haven't felt the whole tank yet? It's impossible. It's like asking you to go in and find out how big the room is, but you're only allowed to look at one wall on the side and a wall in front of you and estimate the whole room size. It's impossible. It can be anything from that area and beyond, right? So everybody gets that, I think. So that's why it's like, but a lot of people don't realize that that's a very fundamental assumption with any flow material balance technique. So that's why it's important to keep your the tongue straight in the mouth for that. Awesome. When it comes to the diagnostic plot, it's very simple. Some straight line points on a graph. The inverse of that is your pore volume. So this is a small OIP, big OIP, or big OIP. And everywhere I put OIP, you could have put OGIP. It doesn't matter. Again, you can use this for gases, oils, multiphase fluids, you name it. The inputs are PVT, rates, and production data. Sometimes you'll see some of the softwares also have inputs when it comes to these methods where they have input of porosity and height as well. The reason why they do that is that they can give you kind of like a acreage, like a surface, basically an area at surface that they convert into, such that you can kind of use it for wall spacing and these kind of things. But that's the only reason why they do it. It had nothing to do with the method and the pore volumes themselves. The equation looks a little bit scary at first. But if you break it down, this is an intercept right here. This is material balance time. This is pore volume. So far, so good. An intercept on the y-axis, let's just forget about it. The material balance time, that's just a time function. If you've done any type of RTA, if you were in the RTA course, if you went to Texas A&M, if you've met Tom Blasingame, everybody knows what material balance time is. Pore volume is what we like to estimate, and that's what we talked about all the time. That's what we're here today. We'd like to find out how much of what's down there from this well can we contact with the method. And then on the y-axis, it's getting a little bit complicated at first. This stuff right here is mass rate. So that's oil, gas, and water converted from their actual volumetric rates with density. Density we get from PVT, and we then convert that into a mass rate over time. So far, so good. But then we have this thing here, which can be a little bit abstract at first. It's called mixture density change. So it's just the mixture density at the initial conditions versus whatever it is at the wellbore. Kind of the same as when you do the, you do PI minus PWF if you do RTA. But what is mixture density? So mixture density is just if you have this cup right here, maybe you guys see me on the screen or not, and I don't know what it says there, but hopefully it's something positive. But if you take this cup, oil, gas, and water in the cup, the fluids, they don't segregate, or they don't mix, sorry, but they segregate. So you have oil probably in the middle, water, and then gas at the top. But so they don't mix, but you can still measure the volume of the cup, and you can measure the mass of the cup, and you can calculate a pseudo density, and that's really what this is. So if you took mass rate now, multiply that on the right side of the equation, you'll realize that you're actually just looking at a kind of complicated version of this one. So, and this is one of the equations that one of the few equations I still remember from school. The second thing is that it's a linear relationship, which is every engineer's dream, to have something super complicated, nonlinear PVT, superposition, you name it, and just simplify it into a linear type of equation. Okay, so that's the crash course for multiphase FMB. You know the basics at this point. Some of the basics will repeat, but we'll spend more time, most likely, on making sure that we know the practicalities of interpreting the plot. The second thing that maybe I haven't advertised that much, get some critique for that, because some people really love it after they see it, and that's this recovery factor analysis feature in the software. So if you do any type of recovery factor work in the software, you'll see that when you have the multiphase FMB, there's this recovery factor analysis feature. And if you haven't used it before, that's what we're going to talk about today. So multiphase FMB gives you the size of the tank. That's what it gives you. But we still are missing one piece to give us an estimate of our EORs. And that's recovery factor. So if we have recovery factor and the contacted pore volume, that's how we get our EORs. And this EOR would then be physically constrained. So that's what that whole workflow is related to, and that's we're going to go through all the tech, like all the theory and details of that now and a little. Any questions so far? Seems like this is good so far. That seems solid. So I'll just continue. If there is any question, feel free to just stop me at any point in time, and we'll touch upon it. Okay. We have two things that we're going to do today. Method to estimate the size of the tank, and the second thing is to get some recovery factors from that tank. That's only two things we're going to talk about. That's why the course becomes a little bit short, because there's no magic going into this. So on the theory part, the multiphase flow material balance without rel perms was introduced by Leslie and Barry that we talked about. They worked on this for 5-6 years. I think even Cimerex had it quote-unquote proprietary internally for years as well. They use it religiously on every single well that they have, and I've seen other companies are picking it up as well. Basically, this combination of doing multiphase FMB and the recovery factor analysis. It's a very simple plotting technique to analyze multiphase production data, and it outputs the pore volume, oil in place, gas in place, and water in place. And the only thing it requires is PVT, production data, bottom hole pressure, and reservoir conditions. So it's beautiful from that perspective. As I mentioned, does not require rel perms. Outputs the pore volume, does not care about geometry. So that tank can be looking like a star. It can be looking like a rectangle, triangle, sphere, ellipse. It doesn't care, but it assumes that whatever that tank is, it's boundary dominated flow. So in many cases, you'll end up using it to bound your RTA work. And again, inverse of this, that's your pore volume. Awesome. The next slide is just for reference, so you see the slides in the slide deck. But of all these moving pieces here in the equation, I did not actually say how they're calculated. So the next slide comes with a warning. That's only for reference to try to make the course complete. You don't have to try to digest it or anything, but if you wanted to calculate these things yourself, it's very easy to do. And you use these equations right here, which I know makes all our brains hurt. But if you break it down a little bit, it's only what's plotted on the x-axis and what's plotted on the y-axis. So if we start with the y-axis, the mixture density, that's just, this is for the mixture density for oil, for gas, for water. So that's just PVT properties. That's what it is, really. Then we have mass rate, and mass rate is just mass rate for oil, gas, and water, right here. That's how you get to that. That's very simple. You convert density or rate to mass with density. That's it. That's only two things you plot, and then you use those together, and then you have material balance time. But that's just that's just a cumulative produced divided by the rate that day, and that's what you plot on the x-axis. So that's what you use the mass rate for. And then you get a plot like this. And if you take the equation, The y-axis is the stuff in green. On x-axis is here. That gives us a slope, and it also gives us an intercept. That intercept is there. They tell me that intercept should have some kind of physical significance. I haven't done enough work on it to it's kind of like a multi-phase productivity thing of some sorts, but I'll let the experts handle that and talk about that. But what is the primary objective of the multi-phase FMB thing is the pore volume. So that's whatever that slope is. So we need to have a practical toolkit for us to be able to tell us what or how we should interpret real data. This is obviously a vanilla envelope version of the data created with some simulations, which I'll show also in a second. So in practice, we have this plot right now, and I've shown some equations and stuff. We kind of covered some theory. We're getting a little bit warm and fuzzy. If you've done this in the software before, you might have, you might be familiar with some of this. But what's important really is how you practically interpret the plot. There's a couple of things to remember, but not too much, and you'll be off to the races, and you become dangerous really fast. The first thing related to the practice is, and we're going to use real data, real case studies data for this, is the 3 periods that you very typically observe. There is a period, and this is primarily for oils, okay? And we'll talk about this. For gases, it's typically only 2, but it can depend a little. The first period is a slope that you'll observe while you're still in above the saturation pressure. So I plotted the bottom pressure versus time and the saturation pressure on the plot here. As long as the pressure is above that, will be single phase oil and water in the reservoir. When it's only single phase oil and water, the compressibility of those 2 fluids are small. And when the compressibility is small, you're able to observe boundaries much quicker. Okay, so that's, if you remember back to the radius of investigation equations, if you looked at the time to end of linear flow equation, if the total compressibility goes up, seeing or feeling boundaries will take more time. I didn't invent that. That is Mother Earth, but that's how it is. So what happens is when gas is coming out into the system, the total compressibility of this plot or of the system goes up. So this, the signal to basically be able to see that boundary will be delayed. So you get this transition period, which never is the correct slope, by the way. And then you start to get more gas, or then you're basically able to feel the boundaries while you have the gas in the system, and that will be your second stabilized slope. And in this case, you basically see, maybe you can see it visually, that the initial slope and the late slope is the same, which means that it was in boundary dominated flow before it reached saturation pressure and later. So like the whole tank was observed already before it hit saturation pressure in this case. So this was case study number 1. Case study number 2 is provided right here. That is from the Permian. And when you have this case study right here, you can see the typical example. We have 3 slopes, and which slope should you pick? And I'm going to draw some slopes, and I'm going to make my first QC. And this is the first knowledge that is probably important if you haven't done this before. The first thing that you need to have in your reservoir engineering toolkit, the average reservoir pressure of your tank can never be below the bottomal pressure of your well. It's impossible at the same time as you produce fluids. So we always check that the bottomal pressure, that is to the right here, is below the average pressure of the tank. And how can you get an average pressure of a tank? That's a great question. And the answer to that is if you have assumed a tank size. So if you picked a slope, then you have picked a tank size. If you have a tank size and you fill that up with a fluid, and then you're removing mass from that fluid, that's essentially what you're doing with the surface rates, right? You're removing oil, gas, and water. So you're removing oil, gas, and water from the tank, and once you've been able to do that, the pressure in the tank needs to change to be able to make sure that that's at constant volume. So that's just a pure PVT/material balance exercise. So that's very simple to do. So every time you pick a slope like this, you can back out an average pressure. That's what we're doing right here. And that's the most important QC, and you would like to make sure that this line, the yellow slope, and whatever the average pressure here gives you a average pressure that's above the bottom wall pressure. If we pick slope B, what will happen is that we'll get a average pressure that's below the bottom wall pressure. So obviously this slope is not correct. And then slope C, that's when we've seen probably more of the reservoir volume. In this case, that's a little bit shallower than slope A, which means that it's a bigger pore volume. Hence, the average pressure will be larger versus time. Now, these three slopes, slope C is the number that you should pick. So always pick the shallowest observed slope. That's the kind of lesson in general for this. The second thing here is related to buildup. So if you have a buildup in your data set, you can go ahead and try to honor that when you're doing your analysis. So here you see kind of just from the pure data, the blue data to the left, you see that there is only kind of two, at least I kind of see two different slopes. It's the initial slope, which is slope A. And this is for a well that's saturated in situ, by the way, so you go straight into like the three-phase parting. So there's no of this like single phase period. So you have slope A, that you see right here. And so with slope A, we can back out a average pressure versus time. We see that this is not correct. And then with a little bit more time, these are gauges, by the way, so we know it. We can get slope B. Slope B gives us this average pressure versus time. This average pressure versus time is actually going through the buildup there. So if we did not have the buildup, this would actually be an okay analysis of us. And just mind you that all the points on the plot to the left, all those points, they're associated with a drawdown because I'm plotting mixed density change over mass rate. So there's a rate here every single day. And when that rate is there every single day, the buildup data points, they will never show there. So in those special cases where you have a buildup that you trust and you think it's accurate, you're actually allowed to pick a slope that's shallower than what you see on the screen. And the reason for that is that you as an engineer have been tasked with the exercise of estimating the contacted pore volume. In this case, it will be a minimum contacted pore volume because obviously this well is still infinite acting or transitional. So your job is to pick whatever the slope is that gives you an average pressure that is higher than that build-up pressure. So the slope C would actually be the correct slope in this particular case, and we would expect that these blue data points will most likely later point in time here at least get onto that same slope. So that's just something that will happen later. That would typically for a well that's infinite acting or transitional still. If there's a call it a buildup or call it a buildup from a frac hit, we should just go ahead and ignore it and not use it for at least primary depletion type of work. So any type of external source depends a little bit on what you want to do. I'm going to look at a refrac example later. If you actually want to quantify the uplift from that, then go ahead and be my friend and use it. If not, we should be you should just ignore it. And if you're still infinite acting or transitional, that's what you are. Then you can go ahead and use, or then all the numbers that you'll be picking will be lower estimates of the contacted pore volume. So initially you'll pick a low pore volume. Over time it will bend over and become steeper, and eventually will converge to the actual pore volume, like that. Okay, so that's basically what you'll end up with. For conclusion, pick the shallowest observed slope, the largest pore volume observed. If the buildup data is present, adjust the slope until it just honors the buildup data. And if a frac hit is observed, the part of the data should be ignored. And if the well is still infinite acting, then the multiphase FMB just provides a conservative estimate of the pore volume at hand. Any questions related to this? Was this fairly okay? Feel free to shoot a question in the chat here. but getting close to the break here, 10 more minutes. So in the theory part, for recovery factor analysis, we know again that the multiphase FMB is only trying to give us this, the pore volume. We talked about that already, size of the tank. And what else we need is the recovery factor, that will give us the EOR. And the equations for that is given here. The EOR of oil, that's oil, like concentrated oil in place for oil, multiplied with the recovery factor. Similar for gas, similar for water. So in the software, from the multiphase FMB method, you get this guy, and then there's a workflow to get the recovery factors, and those are provided here. That's the recovery factor numbers here to the right. Okay, so if you have both of those, you will be able to kind of get a physically constrained EOR decline type of, or an EOR that you can use to maybe try to match your declines, for instance. And this is physically constrained. So when it comes to recovery factors that you calculate from the material balance exercise, when you do that, and we'll talk about this a little bit later, there's 3 different ways in the software that we calculate recovery factors that we'll show. And they all basically use the same methodologies. It's all accounting, and they basically use these equations from Walsh and Lake's book, which looks like this. I don't know what's happening in everybody's brain now. It's essentially this that's happening. But if you look at these equations, actually what it is just saying to you that the recovery factors at an abandonment pressure is just a function of the PUT at the abandonment pressure, the relative ratios at that abandonment pressure for both oil, gas, and water. And that's it. That's what it's saying. That's exactly that type of accounting exercise that we're doing inside of the software when you're calculating recovery factors. And the workflow to do that is this recovery factor analysis that you can find up here, or we'll talk about that in the software a little bit later, that dashboard. But again, that's the dashboard that it's brought to you when you go in and pick this. And that's my dog. Just give me 1 second. Sorry about that. It was the sales guy. But just real quick on this, the interface that we're dealing with in the recovery factor analysis looks like this. It has the ratio forecast of CGRs. It has the ratio forecast of water-gas ratios, and it has the ratio forecast of bottom of pressures versus time. And that's what it uses instead of using rel perms. So that's what we're going to go through a little bit later. And the most important part of that exercise is most likely how you forecast your OGRs versus pressure, where the recovery factor of oil, if the OGR versus pressure is low, like this, then you get low recovery factors for oil. And if it's higher, you get a higher recovery factor for oil. And how do you do that forecasting? How do you QC that that's correct? All those things, that's what we're going to go through in the course today. A lot of people here ask why you need rel perms for this, or why rel perms are not needed for this particular exercise. The reason why it's not needed for this particular exercise is that rel perms is needed together with PVT properties to give you fluid ratios. But if you looked at the last slide here, we are actually forecasting the fluid ratios ourselves. So that's the difference why the forecasting piece in this methodology does not require rel perms itself. Okay, so because we're, if you already have the ratios, and I've been forecasting the ratios just empirically here, I wouldn't need it to get a recovery factor. While in a numerical model, I would need it, and we'll talk about that also. If you want to convince yourself that a producing ratio is a function of PVT properties and rel perm terms, then you can just look at this equation right here. You see that the blue term is a relperm term, and then you have a PBT term, and the combination of these two gives you producing a GOR. Awesome. So in the software, what a lot of people don't realize is that there's 3 different places where you can get recovery factors. And that is in the numerical model. It is in a feature called simple material balance. And it's in a feature called recovery factor analysis, which is the one that's linked to the multiphase FMB. And I'm going to try to convince you that, or I don't know, you can convince yourself as well, but it's very easy to try to do this exercise where you say, okay, I would like to check if they're actually giving me the same answer in all these different exercises. And it's very easy to do because if you have the same assumptions, the results are the same. The recovery factor for oil and the recovery factor for gas will be the same for the same abandonment pressure and also for the same cumulative GOR or CGR value. Okay, and I'll try to convince you guys of that in a second. So in courses here, I'm going to just, this is main, so I'm going to go ahead and pick my project here. And we're going to go ahead and create projects here just after the break. I just want to make sure that, yeah, so I'm going to create an oil well here, and then I'm going to give it some PVT properties here. And then I'm going to go and do three things. I'm going to go ahead and run the numerical model. Just want to make sure that I'm in full boundary so I can use these methods. So I'm just going to remove any volume beyond the frac tip, and maybe I'll just increase the rel perm a little bit, like, or not rel perm, but the permeability in the numerical model. So now I'm having a rel perm set here that the method doesn't know about. I have an initialization in PVT, and I can take all of these simulated rates here. This is around 1,000 days, and I see the average pressure and the bottom of pressure. So we for sure this well is in 1,000% it's a boundary dominated flow. So if I do what I just did now, click export, and then say set historical data equal to simulated data, I upload the simulated data as production data. So like we can pretend that this is the production data for this well right here. Then the thing I can do is to go in and run the multiphase FMB, and then I can check, okay, is the multiphase FMB actually giving me the correct pore volume? So I can take this pore volume here, 3.6, and I can type that in here, and I see, okay, it's perfect overlap in terms of the slope on my data set, exactly the same slope right here of the data. The feature here, the recovery factor analysis feature, that I'll show you guys how to use later, but the very quick and dirty way of doing it is just to do something like this. And then I think I need to be very precise here. Let's do something like this. I could probably do something like that as well. Anyways, so I'll just go ahead and run this. It just needs some forecasts here. I don't really care about water for that. As long as I have this, I can put my final pressure and something like this. Go ahead and click run. And then what the objective of this recovery factor analysis item is here is to give me these recovery factors, these guys right here. And these oil recovery factors that we see over here, they're 28.15 and 61. And in my numerical model, 28.15 and 61.1. So that should be close enough. So those are like full multiphase. As long as you remove the same amount of oil, gas, and water, the recovery factors will be exactly the same. So that's the 2 methods. That's basically this guy right here and the guy over here. So they give the same results. And then there's a method called simple material balance that maybe some of you guys know, but it's down here. And the only input to that material balance is an abandonment pressure and your cumulative produced ratio. So a lot of people take like their DCA forecasts, their oil and gas DCA forecast, cum them, and just do that ratio to get some recovery factors to sense check whether their results make physical sense or not. So in this case, we had an abandonment pressure of around 1,000, and we also had a 2170-ish. And there's no water phase here, so it won't be 100% compliant, but 6.1 was something like this, or 2.1. 70, was it? No. Anyways, something like this. I'll show you how it works. So this is basically how this calculation works. The recovery factor is 27 and for oil and 59 for gas. And we see that that's a little bit less than the recovery factor in this case, which is 21 and 61. And the reason for that small difference is that in the numerical model, there's a rock compressibility and there's a little water phase as well that is accounted for in the flow material balance recovery factor and the numerical model recovery factor. And the simple material balance is just assuming no rock compressibility, and it also assumes no water. But in terms of order of magnitude, for all practical purposes, exactly the same. Great. So with that, we're going to take a 10-minute break, and after that, we'll start with some case studies. And we can also do some questions after that, and we'll make sure everybody has some data and whatnot after that. In the break, if you still have an issue with logging into your account, please let me know here in the chat. I'll fix that in the break. Okay, so we're back again. Just very quick in terms of just making sure everybody got logged in. I saw a couple of people. I got some help. Chad, were you able to log in okay?
Yep, I got it.
Perfect. So what I'd like everybody to do now is to make sure that they're inside of so in the software right here, a couple of things. Just make sure that your Zoom, if you're on a small computer, see I'm on a really small computer today, that one that I'm sharing at, and just make sure that you put the Zoom in here, so at 50%, or something higher, depends on the screen size. Just do what feels good, but typically 100 is too large unless you're working on a really big screen. In this environment, click the FMB course here, and up to the right, make a project that's called your name, and then just FMB course. And I'm gonna make this 2 since I did this also earlier today. Okay, I'm gonna show that one more time. Make sure that you go to the FMB course. In projects, up to the right, type your name. So that's this button up here. Add project, add your name, first name or whatever, and then FMB course. That will be the name. And when you're done with that, just find the course, and then that's where you're going to be. We're going to upload some wells, and I'm going to send that to everybody here. The details of the wells that we're using is not really important for what we're going to do today. The primary thing is that we just have some data. So this link right here, copy the link. I'm going to paste that link into the chat. So if you click this link right now, that will download on your computer. So then your only job would be to go mass upload, find that file on your computer right here, click save, and then you have the wells there. That's where we're going to do the work. We're going to use these later, but I just want to make sure that everybody has that. So I'm going to show that one more time. Go to the chat in the Teams. So the chat in the Teams. Click this button right here. That will download an Excel sheet. Save it somewhere where you can locate it on your computer. Make sure that you're inside of your project here, field, project, and then in the project, click mass upload, and just drag and drop those data points in here, or that Excel file, and just click it and locate it on your computer. Perfect, and then you should have 3 wells there. If that didn't work for you, just let me know in the break, and we'll make sure, because we're going to do the exercise in the last section. So if that didn't work for you, or if you did not, if I did it too quick, we'll just go ahead and do it together after the break. Okay. Any other questions related to what we talked about before the break? No. So pretty good so far. So what we're going to go ahead and do now is just a few case studies. Every single week, we're sending out this kind of newsletter thing. We're just like, what's next and whatnot. Many times we send out a PDF attached to that email that has a bunch of case studies. Some of them are related to, some of them are done in the Bakken, some of them are done other places. Okay, so you can use that also for MFMB, and you'll see some of those old recordings presented by other people than myself, so like actual operators and stuff, and they're really cool the way I think about it. Awesome. So the first thing we're going to go ahead and do is going to look at a case study in the Permian. It's a well that's a lot of things is going on with. We're going to apply a few of the things that we've learned so far, and we we'll see a Eagle Ford case study, and we'll see also like a multi-well case study as well. So if you have any questions, feel free to shoot at any times. The concepts should be the same in every single basin. It also will probably highlight a couple of key things that you can put onto your reservoir engineering tool belt. And I think I promised 3 things, and we've learned 1 already about the average pressure versus the bottom level pressure. So example 1, so that's a Permian case study. So this is a case study that was presented by Coterra a couple of years ago. I'm gonna just do like this. And it's a well that has a lot of things going on with it. It's a parent well that after probably 2 years of production, a infill well is coming online, and then there's a couple of workovers actually on the well. So that's what we've highlighted here. So just a few wells. The well, we used the Multiphase FMB to analyze the well. It is an initially saturated oil well. That means that we don't have this period where we have two call it low compressibility fluids that we can use early. But it has a downhole gauge. That's great, so we have accurate information. And it has approximately 5 years of production. 2 years is approximately 2 years is the period of time when the parent is producing before the infill wells were drilled, and then there was these 2 subsequent workovers. The quality of the water is sometimes questionable, but initially the water saturation is assumed to be 30%. The first time they did multiphase FMB on this particular well, on the parent well, that was before the infills. So if you go back to that case study that Coterra presented on, that's basically what they're showing there. And the initial analysis had a water saturation that was assumed to be 30%. So if you go ahead and do that analysis with a water saturation assumption of 30%, and you do your best job at interpreting this type of plot, you get the dashboard like this in Whitson Plus. One difference that you'll see here is this purple line. By default in the software, that purple line is off. So let me just, these are searchable, by the way, so it's really handy. So I can just take, when you load the dashboard, there is only one line. It's a blue line. But the legend here is hidden, and that's off by default. And that's a purple line, and that purple line should always go through the origin. And all the blue points should always be to the left of the purple line, unless there's some bogus data points that we don't trust. That's always the rule. And what does the purple line represent? Well, the purple line represents basically this mixture density change at the average reservoir pressure. So of course, then you would have to have an assumption of what the tank size is first, then it back calculates this one. So it would be essentially the most effective way you could deplete the tank. So think about it as if you had a piece of rock, and from day one you were able to just obliterate the whole rock and able to contact and drain it from day one, and there is no transient from low permeability rock systems and these kind of things. That would be what this would represent. But that's what the toggle is and how you get it on. I usually don't have it on, but I just wanted to mention that. The interpretation of the slope is seen here. This is the black line on top of the blue points. And then you need to make a few checks. The first check is all the data, the blue data, above the purple data. And that checks out well. That looks good. There's some early time water quality data that might be bogus. The other check that you like to do is to make sure that your average pressure is above all the bottom pressures. These small points right here, they're assumed to be just bad data, but these kind of buildups like this is something we'd like to honor, and it checks checks out that box as well. But then we go to the water. And this is the second thing that I wanted you guys to have in your little engineering tool belt, like an additional, call it an additional tool in the toolbox. So here we see that the water saturation is changing 30%. And then the question should be, really, do we expect that the water saturation should change 30%, or okay, maybe not 30, but almost, like it goes from 30 all the way down to 7. Then you need to make a couple of reminders. So water is very incompressible. So water can be only produced by 2 different mechanisms, and it's displacement, which this is not, and it's expansion. So your water saturation, if you actually run these models like a synthetic model and stuff, your water saturation should actually not change very, very much. Probably in the single digits, even if you have frac water in the model there, single digits max. So this was something that these guys was like, okay, this sounds not right. So we need to go back to the drawing board. So the analysis seemed that it was consistent on most parts, except from that there was a huge change in water saturation. So there was 2 different ways forward to do this. The first thing would be that you could go and reevaluate the water saturation assumption with the petrophysicists and geos. And you could also go ahead and do the analysis without water. So in this case, they ended up actually doing both. So they ended up checking with the petrophysicist, and they came back and actually realized that they fracked layers that had a higher water saturation, and that they thought initially. The target formation maybe had 30% water saturation, but they were targeting a lot of other things as well. They also, so they basically increased it up to 70% and redid the analysis. When they redid the analysis now and they checked the water saturation change, it went from like the, it was like the 70s to maybe 64 or 63 or something like that. So it passes the smell test. Was 70% exactly the right number? Probably not, but it's at least a heck of a lot better than 30. Then they went out and did the analysis without water. And that's a feature in the software where you can go in here and say, I want to exclude water. And when you exclude water, the mass of the water in the tank remains constant. So there's no water expansion, and the water saturation will change only slightly as a result of changes in rock compressibility. And this will provide the most conservative estimate of your hydrocarbons in place. So this will be kind of like a lower estimate. Again, when you go ahead and do the analysis, the nice thing about using this option, especially if you have questionable water data, it removes a lot of noise. So you see the signal is clear here because we typically care more about oil and gas. And there's also there's no kind of shallow period early. And we'll show all the comparisons later. Then after the well was like, there was infill wells there was some workover, etc., etc. They analyzed the well again, and you could see that after the workovers and after the infills, even when it was stabilized, that the rate data came back to the same, or the slope became more or less the same, just changed, maybe shifted up a little bit and down a little bit. And then the question is related to this. Is this okay? This pressure support, actually, this was an interesting case because the fractures energized the parent. So this is kind of like external forces that was not a part of the tank. So they, in this case, chose to ignore it. If you use this methodology maybe for a refrac scenario, then that would probably be different. But this was not a refrac, it was just infill wells. And of course, the objective was not to look at changes in pore volume for this. The last check that you need to have in your tool belt, that's then it's getting really advanced. So now you're becoming like a multi-phase flow material balance OG, if you like. So with these slopes right here, if they are not parallel, so now you see that it's kind of hard to see maybe on this graph right here, but you see that the black line and the purple line, they converge a little bit. that could be an indication that you're about your rock compressibility. So when these two guys are not parallel, they indicate something. So if the average, basically purple line, is too steep, then the rock compressibility is too large, and if it's the vice versa, the rock compressibility is too small. So what they did was that they updated the interpretation to reduce the rock compressibility in this case compared to the default, and the lines became parallel again. So when it comes to the summary of this, when you did the case originally, and I'll focus on kind of this point right here, the oil in place. Of course, the water in place will be really affected by if you assume that there's water there or not. But the oil, if you have a 30%, it gave you 2.4 million FCB. At 70%, 2.3, and then with no water, it gave you 2.1. So that is what I talked about. If you ignore water, you remove a drive, that will always be the conservative estimate of your pore volume. Yeah. So KP is asking when in the no water case, you still have an assumption. So in this case, when there was no water, that no water case is like in that tank, there's no water saturation. So I think if you go in and run it in the software right here, and I go and put in and 0 water, exactly. So there, it's still 30% water in the tank. It's just that it doesn't move at all. So you'll see that it's constant, basically over time. The only reason why it's different is because of the rock compressibility versus time. And the second question is why the oil in place is almost the same for 30% and 70% water saturation case. That is a good question. I actually wondered about that myself, but I guess it's probably just so this plot right here. That's the interpretation with 70% water, and here's the interpretation with 30% water. So for this case, I guess it just ended up being that with that input. But I would think it would be the a little bit larger, but hard to say in general without looking at it more. Awesome. The very good. So the second thing is that we're going to go ahead and look at a case study that Devin presented for UTEC. So that was Stephen and Trevor wrote a paper called Using Multiphase FMB to Evaluate Refracts in the Eagle Ford. And the methodology was presented there at UTEC, and I'm going to show kind of the key part of what they did. So the first thing that these guys went ahead and did is that they created a synthetic example. They took a simulation model and added and doubled the number of fractures, basically. They doubled the contacted pore volume after a period of time. And then they fed this contacted pore volume, this new superposed kind of model, into the multiphase FMB method to just make sure that they felt good about it. Does this make sense or does it not make sense? And when they did that, they simulated this in the software to get these oil rates versus time. That changes when you get at the refract part right here. And by design, we just wanted to make it simple when we ran the simulated case. We just wanted to make sure that we 2x the contacted pore volume. When we went ahead and did that, before the refrac, we got about 3.5 MSDB, and after the refrac, 7 MSDB, which was exactly what we put into the model. So that makes us feel comfortable that the methodology captures this delta and uplift in the models. Then for the Eagle Ford, what Stephen and Trevor did is that they had around, I think they have around 40, 50 refracts. And then there was some data issues and whatnot on some of them, so there was probably around 30 that they could actually go ahead and do this type of analysis on. And that was done, so in the Eagle Ford, where you have a wide range of different fluids, etc. So it's important to account for these multiphase effects. So that's why multiphase FMB was used. And again, this reminder that they were typically seeing, we typically see 3 different periods: an initial straight line portion of the data, the transition period, and then the late time portion of the data. And again, just a reminder, this first part of the data, that is during the single phase flow period. Then you have a transition period, and then you have the second stabilized slope. If you're dealing with a gas condensate or like a gas system, then many times you just go straight to slope 2 and then 3. So when you have these 3 different options, what can happen is that you have a early slope that is steeper than the late slope. And that means that you have a early OIP that's smaller than the late OIP. That just means that you're still infinite acting early on, and then you go into boundary after late time. Then you might have a case where your slope initially and the slope late time is the same, and that just means that you've contacted everything early. And then the third one would be that you have an early contacted oil in place that's actually larger than late contacted oil in place. And that could happen if you either lose surface area with time, or that there's a strong geomechanical effect in your system, or maybe both. That's something we see a lot in the Eagle Ford, actually. So that's a little side note for you, those of you who work in the Eagle Ford. So number 3 is actually the reason why they analyze both, call it early slopes, pre and post frac, and late slopes, pre and post frac. So if this is your case, that your surface area is actually changing over time, of course, then your true contacted pore volume is like probably a mix of those two, somewhere in between, what you're actually effectively draining. So just to give you an example of this, if you just went in and did multiphase FMB on a well in the Eagle Ford, you can have an oil in place early that's 2 million STB, and then late time it's 600 MSTB, even though that well has been producing for years and years and years. And that's because of this artifact that you have these very strong geomechanical effects, which seems like there is some consensus of, at least with the Eagle Ford companies I talked to, or that you're losing this surface area with time, and that's different than a pure boundary effect. It's different than a pure boundary effect from that perspective. So in practice, you're then dealing with, in this scenario, you then will be dealing with the contacted pore volume that changes over time, and probably for like a recovery factor analysis type of exercise, the contacted pore volume would be some number in between these 2 extremes. So that makes it a little bit special in the Eagle Ford. So that's why when they analyzed a refrac, they took this is a successful case, if you like, where they looked at both the EUR estimates, post and pre-refrac, both early and late time. So early time, was almost a doubling of the contacted pore volume, and also late time. You could do that similar exercise with a not successful refrac, like this, and you would see that there is almost no delta in the difference between an early and a late time. So, and the reason for that is just that it wasn't so successful in this case. And they did this type of analysis on every single well. I think it was 29 in total. And they compared the early time slopes, pre and post, and the late time slopes, pre and post. And on average, both of them actually gave an uplift of around 80%, which you see here. And then you had some that was more successful and some that was less successful. In general, what they built with the early slopes was this correlation between uplift and EUR for the wells that they've been producing for a long time, and this slope difference right there. So with this correlation, they could then just use with the first 15 days of production data. This is like a diagnostic plot to say what the long-term effects was. So the early time slopes, they just used 2 weeks of production. And when they did this, because they used the multiphase FMB, then they're accounting for this complex combination of multiphase flow and superposition, which is important, especially because most refracs are done as the wells are below the saturation pressure. So you get this complicated mixing. There's also a nice tool that they use to kind of differentiate a little bit between what is at least, call it added reserves versus just acceleration of production. Very good. Any questions about this? I see there's some chat questions. Let's see. Is something else compensated to account for the difference in SV? Is that related to the last case study there, Tarun? Yeah, correct. Something else compensated to account for the difference in SV. In that case, not that I know of. I need to maybe double check with Barry or Leslie and Barry on that. But it's a good question. Yeah. The last case study that we're going to go through is related to multiphase FMB on well groups in the Permian. And then after that, we're going to go through a couple of small things, and then it's a break, and then it's just some exercises. So example 3, multiphase FMB on well groups in the Permian. We're going to start also here. This was presented by Barry and Leslie for RUTEC as well. Another paper there. It's well groups in the Permian. Synthetic example is this example right here. So we wanted to first make sure the theory matching the practice. And here the parent looks like this. It's being produced for a period of time, and then we put in 2 infills. And what happens is that if you produce a parent for a period of time and it's a high enough perm, then even there will be some contribution here in this part right here that will flow into this well. So the parent will kind of come in, or the first child will come into like an already depleted part of the rock. So that's the challenge here. Are we able to capture that with the multiphase FMB? So what we did, we ran a simulation of a parent up to around 2 years of production. And then we added a couple of infill wells, as you saw in the grid. And then the density distribution then at 200 days is the blue here is very well stimulated and drained, if you like. That's within the frac tip. And beyond the frac tip, we have kind of a saturation change. Close to the frac tips, there's a lot of drainage, and then because of it's higher perm, but it's not stimulated. So at least my gut feeling when I see this is like, okay, if the MFMB method works in this scenario, the first child well should pick up a smaller contacted pore volume than what it is its own SRV, if that makes sense. So and that's because it's the blue one should have stolen some of that production. So my guess is that like the contacted pore volume of the parent will be higher than its SRV, and then the first children will be lower, and probably the one all the way to the right won't really care because it doesn't look like the saturation has changed. So there's a couple of ways to do this. The first way to be able to do it would be to go in and do the workflow just individually on all the wells and just superpose the results. And if you go in and do this on the synthetic data, and we'll take a look at the real data a little bit later, it will look something like this, which you see on the screen right here. It might be a little bit small, but that's just interfaced in the Whitson Plus. And if you did that, the parent would give you 4.5 million reservoir barrels. Infill 1 would give you 3.7, and infill 2 would give you 4.3. So as I mentioned, the parent takes a little bit more than SRV, infill 1 a little bit less than SRV, and infill 2 about what the SRV is. If you compare this to the actual mapped in place volume for the synthetic model, it's very close, around 3% off. So it's at least the synthetic simulation works okay. An alternative way of doing it would be to create a pseudo well. So you would go in and take all the rates, you would add them together into like a super well, and then you would mass weight average the bottom pressures. So you would take the bottom pressures over time for all the wells, and you will just weight them by mass. The benefits of that is that you can reduce some noise, you can get a clear reservoir signal, etc. And except from that, everything else in the method is exactly the same. And if you go ahead and do that, you'll get 2 different stems, one pre and post when the children are coming online. You see the children line is what we see on the slope right here. And the contacted pore volume from that exercise is 12.1 million reservoir barrels for the whole, call it pseudo well. That's around 5% off the actual answer. So a little bit smaller, but we're really, really good. So if we went in and applied this to the Permian, like an example in the field, then we actually don't know what the answer is. So maybe the safest is to actually just do both methods. So maybe that's not a bad idea. So in the Permian, you have a wide range of fluids. This is on a pad where the fluids are fairly similar, and you can do all these exercises individually and add them together. And this is an example of how that looks like for a bunch of wells at the same time. And what you can see here from most of these cases, it's saturated reservoirs. So you go straight into the two-phase party. There's not three slopes. There's typically just one slope on all of these different graphs. The alternative to that would be to go in and create the pseudo well. And if you go ahead and do that, the yellow would be the highlighted part of the data before you go or you get these infill wells on, and then you have the part of the data that's after over there. And if you did this exercise, you see the pore volume up here to the right, and you can compare them. That the reservoir pore volume in exercise 1 will be around 152, and the pseudo well will be 155. So very, very similar, similar order of magnitude, off by 3 million reservoir barrels. At least a way to bracket the answer right there. So that's an example of a case study that was presented at UTEC. Very good. The last thing we'll do before we're going to jump into the exercises, an exercise will be kind of fun because they'll be very quick, I think. But it's just some frequently asked questions. The first question is, in the software, there's two methods. There is the multiphase method, and it's the gas method. The multiphase method you can use for all fluid systems, while the gas method you can only use for dry and wet gases. Okay, so no kind of three-phase in the system. So the auger wall FMB can also be used for dry gases. All the concepts are the same, but there is one practical difference, and that's the auger wall FMB is an iterative method, so it requires maybe a couple of iterations. And I'll just demo this for reference, but they provide you with the same result if you compare it to whatever model. Okay, I'll show that we just or prove that, because I don't like to speculate when we can calculate here. So I'll do course number 2. We go ahead and create a dry gas well. When you create a dry gas well on the PVT in the software, you just need to change the method because there's no GOR to wet and dry gas. You go in and provide on specific gravity. The phase envelope will look boring because there's no two-phase region. And you go into we need to have a test case to test against. I'll just remove the water since it's a single-phase gas that's assumed in the flow material balance for gas. I'll just make sure that this well is going into full boundary, and I'll go ahead and run that model. So shall we have something to compare against? And for sure, this 1 billion%, this is in boundary nominated flow. So we can use the methodologies. And in flow material balance now, you'll see that the gas FMB is picked by default, this guy right here. And here we know the answer already, 14 BCF. So I can just go in here, and I can just type in that number, or I can change the slopes if I want to. I can reset my slope, and boom, that thing is straight on. So that's for the gas FMB. It captures that, but what about the multiphase FMB? Well, the multiphase FMB, we can do the same thing. The slope is essentially straight on here. What does the slope give us if we have all the digits? It's essentially exactly what we have in a numerical model. And this is for dry gas. There's no water in the system or anything. Okay, so if you're dealing with dry and wet gases, I would probably go ahead and do it for both, honestly, just to have some bracketing. because the thing I like with the multiphase FMB is that it's not iterative, while the auger well one is iterative. So you might have to change the slope a couple of times, and then before it converges. So that's 2 cents for me on that. Thing is, what about pressure-dependent permeability? How does pressure-dependent permeability affect my well? Okay, so I'm gonna just show that with like an extreme case. If I take exactly the same reservoir model here, reservoir data, say I take this reservoir model and I just make the matrix gamma 10. That's high, but I'm just going to show you what it does and why you need to be aware of this when you're running these kind of models. So you see, I have not changed anything about the physical properties of the rock except from the gamma, but the shape of the gas rate curve is completely different. And you can also see here at the end of the reservoir here, this well is 100% not in boundary dominant flow. So you took a well with all the parameters. The only thing I changed is to introduce a compaction on this model, and it went from going into boundary easily in the first 1,000 days to probably be in transitional flow late time here. And I can just check that real quick. I can add the data points here. So the first thing I can just, this is not in the scope of the course, but I can check in fractional RTA, for instance, here, that late time looks like, okay, my delta is not perfect 0. Oops, I made it, it's like 0.15 or so, something like that, late time. So it's not a perfect, maybe that was even a little bit aggressive, so maybe 0.20. So that means that this well is not in full boundary yet, and you can see that on the average pressure as well. So when I do then the multiphase FMB and the flow material balance and stuff, I will not be able to see the full pore volume. So 14.7 BCF, I will not be able to see that if I run the gas FMB for you here, or if I ran, I can do like 10,000 in ONIP for this one, for instance. Then most likely it would converge probably somewhere around 10 here, and then or 9.6. We'll see here with the multiphase FMB. If I just run that, so we see that there's we're still, this is the slope that gives me 14, and now, oops, I've delayed it. I'll show you what to do there. Delayed it. Yeah, so this is 11. Yeah, 11 MSCB. So if you're still infinite acting or transitional, you're getting, you see some of the walls, but you haven't seen all of them. So that's what's going on here. So that's what pressure-dependent permeability does to you. It delays these things right here. And for the Eagle Ford, if you have strong pressure-dependent permeabilities, that's the world that you live in, and that will just take a lot of time. So that's just what it is. With that, any questions so far? It's simple. I hope it should be pretty okay. Okay, awesome. So what we're going to go ahead and do now is that we're going to take just a break until half, and that's because I've been talking all day, so my voice is not the best. And then we're going to do the exercises after the break. In that break period, if you have not managed to get your wells into the project here, if you don't have 3 wells into the project here, you need to let me know ASAP, so that we can make sure that that's fixed. Okay, and just let me know if there's anything in the meanwhile. So we'll be back at 2:30, and then we start the exercises just after that. Okay, so we'll go ahead and do the exercises piece now. And when we do the exercises piece, I just went quickly through all the, or I don't know, raise my hand. I went through quickly all the people there, and I see most of you guys have used Whitson Boss many times before, but I will still go through just a couple of very quick things before we start to do exercises here. The first thing I mentioned was related to the zoom, so make sure that the zoom is not 100%. If you're on a bigger screen, maybe 80%, 75 is good. You change that up to the right here, or you can use Control minus or Control plus, like this. The second thing is if you have any issues, that you experience any issues that you think is related to the connectivity, just click Control R, and you can just refresh the page. And the last thing I'll go through is the zoom. There's a lot of things that I'm going to skip. This part into the left here, that's the navigation panel. The navigation panel, anywhere you're in the navigation panel, if you're inside of a feature, for instance, and you click the manual, you'll see that the manual and the navigation panel and the manual and the software is identical. And you'll also be brought in, if you're in PVT and you click the manual, you're brought into the fluid definition part of the manual related to PVT. If you were in the flow material balance part of the software and you click the manual, you'll be brought into the material balance part of the manual. And then yeah, there's a few other things up here that I'll skip for now. Most important, if you have any issues, always contact support@whitson.com, up here to the right. That is, or you can put in a feedback request. And then we'll go through the zooms as soon as we have gone through or gotten to the Multiphase FMB feature. So this was your project, Jude. Sorry about that. I'm going to go to my own. Don't mess up your project. But as I mentioned, all these bars at the top here, they're searchable. Just FYI. The first thing, and I know maybe some of you have worked on these wells before. If you haven't, that's great as well. It doesn't matter if you have. We're here to learn about the clicking of the buttons and whatnot. Just let me know one more in the chat if you don't have 3 wells in your project now. This is the last time I'll give you the option to do it, and I'll just do it for you. So I just need to know your name, and I'll be able to do that very fast. Except from that, I think we're off to the races. So in of these 3 wells, click the kite well, go to PVT, and just open the PVT and click save. Here you see my save button. Didn't see it really well in the view, so I should probably go out. But yeah, so I'm gonna see. What was your? Did I delete the well? Okay, so I think the one at the top there is the. This is your project, right? No, maybe not. Isn't the JK your project, Jude?
No, it's not JK. It's JN.
Oh, okay, it's JN.
Yeah.
That's
yeah, that one. Yeah, thank you.
Yeah, no worries. Isn't the if you?
The production data is not showing up.
It's not. It looks like it here.
Oh, okay. I might be doing something wrong then.
Just refresh one time, and it will probably.
Okay. Yeah. Okay. Cool. Thank you.
Yeah, I saw there was a well there, the kite, the first, and then I double overwrote it and stuff. That was my fault, not yours. So
that's fine. Yeah. Thank you.
I'm sad. Okay, so everybody, just again, I'll show it again. You go to the first one, you click PVT, and that's just to emphasize that you need PVT. Just click save here. We're going to assume that the PVT, the production data, and the bottom pressures, we're going to assume that all that is perfect. Then we're going to go to flow material balance, and we're going to click run. And we're going to wait there after we click run. So again, just PVT, make sure that you're on the kite well. Just click save there, go straight to flow material balance and click run. And once you're there, don't touch anything. I'll go through everything with you, such that you have some knowledge about it. I'll give everybody 10 seconds here. 15, actually, that's what I'm going to do. Perfect. So hopefully everybody is here right now. I'm going to go through everything that you see in the menu here to the left. The first thing is the run button. Everywhere in the software where you need to run anything, there's a run button like this. This is where you can choose between multiphase or gas. These numbers right here are linked to this line. So when I change this line, release it, these numbers will change. Or if I make this line different, or the number different, the line changes. Okay, so they're 100% linked. We'll get back to how we change the line and stuff later. These are just initial conditions for reference, just emphasizing what the input is, and they're primarily set in the PVT, but you can also change them here. The saturations, they're automatically calculated by the PVT properties and your water saturation. So if you want to change any of the saturations for gas and oil, you need to do that in the PVT. This is the raw compressibility right there. These interpretations right here, that's just the intercept, and this is the slope part right here.
Matthias,
Yeah.
from where this water saturation and the gas oil saturation calculated? By some default values, right?
So for this well, we uploaded the SPE data set. So
okay.
Water saturation had already been provided to us. You can set the water saturation for a well in the well header information here. And since this is an oil well, then the PVT says that this is an initially undersaturated oil. So the saturation of oil is 100%, and then the difference between 32.1 and 100%, that's what gives these relative distributions.
Okay, thanks.
Good question. So if I change the water saturation here, of course, that's linked through all the different wells. Perfect. So that's the stuff on the left. And then we're going to talk about this plot right here. And I'm going to start at the top left here and move my way over. So the top left, you see that there's a slope called reset slope, or a button called reset slope. And any of these plots that you're working on that has a slope that you can fit to something, they will have reset slope. Because what can happen is that your slope can disappear from the screen like this. To get your slope back to the screen, you just click reset slope. Or you might have dragged and elongated the slope such that the edge of the slope is not on the screen anymore, and you want to reset that. You click it again, and it comes into the window. The other things here, I'll just show you guys. You don't have to do it, but this is the lasso fit. So if I wanted to do like a best fit of this data here, for instance, I just hover over it and release, and the slope will be a best fit of that data. Another thing I can go ahead and do is to click lasso highlight, and that's a lasso highlight that I can also do here in the pressures. I'll show that later. What's the challenge with these plots here and everything that's in material balance time is that you're changing time functions back and forth. And it's hard to know, okay, if you've seen it 100 times, I know that this is the early time data, and I know it's the single phase portion of the data. But just to emphasize that could be nice by highlighting. So what I'm going to do here, I'm going to go down here. I'm going to zoom into the data. And we'll talk about plots and the zooming a little later. And I can lasso highlight. And I click lasso highlight. I just hover over these data points. And the software then goes like highlights these points, and you can see these points being highlighted here as well. So that's the highlight portion. Now again, I've lost my slope. Bring it back. This slope is locked soon. That was a request by many of you guys. I think some of you guys have been on the call here. What is really annoying with the slope is to be able to change it, you have to wait until your cursor symbol is changed to a hand like this, so you can grab it. And if you're just a little bit out on the outside, you're assuming instead. So for a lot of people, they would be like, oh, the only thing I want to do is to change the slope of this thing. I don't want to assume. And I'm a little bit on the outside, and what happens is that this happens, or that you actually have the zoom in, so you end up like doing things like this. So that's why if you have zoomed into a place where you want to fit the slope, and you made sure that your slope is in the view that you like, you can click lock zoom. And that's a feature in every single plot now. That means that I can't change any of the axis unless I type it in, or with like just dragging. And I can't do the drag and zoom thing. So the only thing I can do now is to change this axis. And if I click someone on the outside, it doesn't do that annoying thing. That's what this does. This is export to PNG. This is export to Excel. This is the old school way of changing the axes min and max. So if I wanted to change that here to be 10,000 and this one to be, for instance, 2, you can do that like this. This is reset zoom. It's also in every single plot. That's the default, whatever the software provides to be the default. So if you messed up, reset zoom. And then we have expand, and expand can be collapsed if you click same button again. So that's the options in the plot here. When it comes to the zoom in general, this is important to pay attention to if you haven't done it before. I repeat it probably every day, but it's very, very important, and it's related to the zooming of the axes. If you just want to zoom into a particular part of the plot, you can just hover over and release. If you'd like to change this value here with a number, you want this number to be 250, you need to go all the way down here until the arrow changes to a horizontal line with 2 arrows. Or if you drop here, it needs to be a vertical line with 2 arrows. So let's say I would like to change this to be 250. I click it once, just left click, and type in a number 250, and I click enter. And the same here. Okay. So if I want, you can do the same on all the axes. You can also go all the way to the top here, and that's how you zoom it. And the same goes here. That goes also for the 0 axis as well. Good. Problem is if you're in between here, that's how you don't keep the origin fixed. That's annoying. Toggle on and toggle off axes like this. That's how you do that. Okay. We learned that we were going to pick the shallowest observed slope on the data. And I'm going to toggle this off. This stuff right here is first of all very messy, hard to interpret. The early time portion of the data is not bad. It's single phase. So that's why I'm zooming into this data right here. I know this is above the saturation pressure because you see it from the signature, and if you've done it a million times, that's what happens every time. There's not, but if you want to convince yourself, you could use the highlight on either of these plots, and we know in this plot right here, for instance, lasso highlight, that is, something you could do here, and this is like 3,000 something. The saturation pressure, we know the saturation pressure is like 2,900. So, so we see that all of these yellow points, they are corresponding with these yellow points above 3,000 here, or 2,900. So that's the data I like to fit. Here it basically follows what you would expect. A shallow slope, and then it sees more of the pore volume, and then this is the shallow slope that it sees before it reaches this this period where gas is coming into the system. When gas is coming into the system, the total compressibility of the system goes up. And the only thing you need to do then is to click run one more time. The reason why you need to click run one more time, the only reason for it is the only reason for it would be to quality check this guy, the black line right here, to make sure that this black line is above the all the gray lines right here. These points we'll just assume are bogus points. I think actually Kimberly's point there is actually really a good one, and I'm adding that to the backlog. So it would be cool to have the saturation pressure actually here as just a dashed line, which you actually have in some of the other plots, but it could be nice to have that here, so you don't have to go back to the PVT feature. In P-plot and FMB. Goodie. So far, I think so good. So everybody here, I get around 800 MSDB. The smell checks that we'd learned about, this looks good. This is okay. Oil saturation can change a lot. I think, this is like the SBE data set, so we were just using whatever they provided us. If this was my well, if I worked in this company, I would ask to go on and check the water saturation, because this looks really, really suspicious in general that it changes that much. Okay.
Hey, Matthias, quick question. When you use that lasso fit, maybe I don't like my selection. I was able to remove that, lasso highlight, but now I can't just go back to the regular zoom. How do I do that?
Yeah, you just, that's a great question. So when you've highlighted, you just need to click this one more time. You see that? So like now you have the highlight selected, and then like this. So now I can highlight like this. And then if I want to remove it to go back to zoom, I just need to, you see this is selected now, I just click it one more time, and then I can go back to zoom.
Okay.
Yeah.
Thank you.
Yeah, no problem. You just kind of need to turn it on and turn it off. We were a little bit like, we were unsure, should we, automatically turn it off when you've put the highlight on? But then you became like, because maybe I would like to highlight, this part, and then I wanted to include, this point, and then I wanted to include this point. So yeah, it's hard to police everybody on that, but that's at least what we ended up doing there. Good. So we have around 800 MSDB. I would, if it was my well, I would go and check this water saturation, but let's not do that. So we're happy here. I'm going to go to recovery factor analysis, and I'm going to do the same thing here. Again, these recovery factors, we're going to use that to compare to our DCA and that kind of stuff. Up here to the left is just the analysis. We can't change it. This is the analysis that we did in our multiphase FMB. These are the things we'll calculate. Basic recovery factors, and these oil EORs will be spitted out for us. This forecast part right here, that's the forecast parts that is related to the bottom pressure. So that's everything from here and later in time. That's what's coming out here. So in the final pressure here, change this to 500, just so you see what happens. So that's basically from here to the bottom pressure, there's like a decline. And all these parameters, if you change them, if you make this, you can make this 1,000, for instance. That's basically what pressure it starts at. Then this starting point will be a little bit higher. You can change the nominal decline to be, less of a decline versus time. In the end of the day, it really doesn't matter. What matters is your final pressure, because that's your abandonment pressure, and that's the pressure that you will run the simulation out to until you get until this pressure. Awesome. So that is the bottom pressure. There's a little checklist here, and the checklist says you need to add OGR and VGR versus BHP. So that's what we're going to do now. All of these plots are the same as the plots, or like a lot of the S options. The expand option is up to the right. Reset zoom, the zooming option, downloading, export to image, lock zoom. But then we see there's two other options here. It's a garbage can, which says remove all points, and then it's add points. And that's what we're going to use. So I'm going to just expand this real quick. T-Swan?
No, go
Yeah.
ahead. I have a
Yeah.
question, but go ahead.
Yeah, 100%. So if you want to add the points, we can spend all time to match this early time data. But really for the model, what is important is what are my ratios from this pressure here and out, from 1,000 and out to 500. That's really this range right here, probably in this range. So that's where we would need to have to provide a forecast of these ratios. And the way to do it, you just start from right and you go left. And here, you can say, okay, this data is really scattery. How do you actually know how to draw these curves? And I'll show you how to QC that a little bit later. And you do something similar here. Water, I'm not going to care that much about. Just make sure that it doesn't go through 0. Just make sure that it flattens out and has a positive intercept. And that's it. Once you're happy with that, you just click run here. And then you get your set of recovery factors and your set of EURs. And instead of using rel perms here, the only thing we've done is to forecast these ratios. And a very easy way to forecast these ratios out for both on the U shape here. I'll mention that I'll get to that in a second as well. That's a great question. Maybe we shouldn't make a U shape for this one, but it won't really matter here. There's the reason why there's a U shape typically to this. For this case, it's at very low pressures. It's just that you always would like to be above this line right here. And that's the RV curve. And the RV curve goes down at lower pressure because the K values of the heavier components, as you go to those low pressures, they are non-monotonic. So they start to go up. So that's why the RV curve in every single example. Yeah. So that is just following this guy. Yeah, that's what's happening here. T-Swan? You had a question?
So, yeah, so recovery factor is 25% is based on 197,000 divided by 800,000. That's about right. Okay, so contacted OIP. So the purpose of doing this recovery factors is only meant for check, right? The reasonableness of the forecast, and what's the purpose of this recovery factor? It's just as a cross-checking parameters, or?
No, yeah. So some companies this is what they use on every single well to forecast, to have a physically constrained EOR for their DCA. So now I have around 200 MSDB, and then I do my DCA here, for instance, to run the autofit, and I check it here, and I have like an EOR forecast of 212 MSDB. So okay, that looks consistent. So that's what they use it for. In general, there, T-Swan.
Okay, fine. I think I have some more follow-ups, but I think we can discuss this in another occasion. Okay.
Yeah, and when it comes to for this data, it's really scattery, so it's really tough. The other wells are simpler, but here, how do you sense check that your forecast of OGR versus pressure has been okay? Is to click this button right here, the GOR versus oil, and then you see the historical data. And here, you know that you haven't done a good job if your GORs suddenly shoot straight up like this, or they go flat like this. What you would like to do is to have it fairly continuous. And here it looks pretty decent, not bad in terms of the future. And again, you can create a numerical model as long as that numerical model gives us 200 or 2,300 in terms of cumulative scuffs per STB. Late time here, it gives us that. Then then we get exactly the same recovery factors in the numerical model or in the simple material balance. So so that's the recovery factors here. There's no magic. There's just accounting. That's Wilson Lake. It's our friends over at UT. So that's how you would check it. Sense check it. I'll show you if it looks really weird, how it can look like then. That's what why I should have locked my zoom there. Let's try to do this. I'm just going to do it for you. What's going to happen is that those recovery factors, they will go way down. And yeah, so now I go to 15%, and if I do the GOR versus oil, you see this doesn't pass the smell check for me. Like here it goes to this point, and then suddenly it shoots into a very different direction. So you know, I need to do something with how I forecast my CG. And that was what we also emphasized in the course, that you know, here, if you look at I think it is this guy right here. This is what dictates the recovery factor for oil. And you know, that can be, in practice, that can be a mix of fluid type, rock type, etc. Right? It's basically well perm driven. Awesome. So that was one well. We're going to go ahead and do a second well now, and then we're going to do a gas well together, and then after that, we're going to call it a day.
Matthias.
Yep.
Okay. Just want to kind of calibrate with you. So I think the whole entire exercise is that if we will start from the NRTA, we do all this is we be able to come out with the contacted OIP and also what is the pore volume of the SRV. Right, we do have the pore volume and SRV after producing for, let's say, 2 years. Then we be able to tell or estimate that SRV, what is in that SRV, how much is that is oil saturation, SOSG and SW at year 2, at year T, at year 3, at year 4. Is this correct?
Yeah, I guess, or the first thing there is like, I know you mentioned the numerical RTA, but like in general, you don't need to do the other workflows to get the answer, like the 2 million barrels from NRTA or whatever. But if you're in full boundary dominated flow,
yeah,
and you do numerical RTA, that numerical RTA contacted pore volume that you resolve and what you get from the multiphase FMB, there should be no difference why they're the same. And I can even make a synthetic case there. I can run numerical RTA. I can pick contacted pore volume in the numerical RTA, and you'll see it's exactly the same in the multiphase FMB. Maybe I can do that in the end as well. So that's just on the consistency part. They're using the same PVT, same bottom hole pressure, all that stuff. But there's no prerequisites to mix them, and in a practical sense, maybe you'll still be infinite acting or transitional when you do the analysis, and then these are just lower estimates. The other question is probably, I don't know if you were related to like the saturations versus time and stuff. I didn't completely understand that, but you could, here what we're spitting out, these are more for QC purposes. That's what the saturation of oil and gas is at the atmospheric conditions, and also at the flowing bottom hole pressure conditions. So that's the only thing there. Okay,
I see that. Yeah, I'm thinking of some other utilities and.
Yeah, maybe there are some others.
All right.
Exactly. That'd be good.
Matthias, one question, in the flowing, your FMB, while putting the slope, why you selected the early part? Why not the late part, which we know that will be the boundary dominated? So what you just selected the initial early part to make a slope.
Yep. So like, that goes back to probably hoped I had emphasized that enough, but I realized probably haven't. So that goes back to these three things right here.
Yeah.
That if you have a well, first of all, in that well, the late time bottom hole pressures and stuff was really noisy. It was hard to do anything with it. If the early time data and the late part data is great, and we are in full boundary late time with the gas in the system, well, then that slope should probably be the shallowest. The problem is if you get gas into the system, which is my interpretation for this well right here, then seeing the boundaries, if it increases the compressibility with an order of magnitude, then the seeing or feeling the boundaries will take an order of magnitude more in terms of time. So if you have a slope that is shallower early time than late time, the de facto interpretation for me is just, okay, with gas in the system, I'm not able to observe the boundaries yet, but I was able to do that while I had a small compressibility early time with just oil and gas. And it's also a cleaner signal. So that is what I would pick there. In the Eagle Ford, if you have this combination of like an early time slope and a late time slope, that shows something different systematically, then it's probably because it also is indicating that there is this pressure-dependent permeability effect, or that the pore volume is closing up on itself. So it could be a combination. But that's why I went in and picked the early time part, because you get this transition period with the gas in the system, then it can take a really long time for you to see the final boundaries when you have that gas in the system, especially if you mix that with any type of pressure-dependent permeability effect.
Okay, makes sense. Thank you.
100%.
Can I ask a quick question to follow up with that?
Yeah, 100%.
So as you know, I'm typically with dry gas or wet gas wells, so I would assume that I'm always going to be in this third set, typically with a dry gas well or a wet gas well, trying to match because we don't have that early flat time.
Yeah, exactly. So what you'll actually see, and we'll see that in the exercise here when we do it, is that you'll just see kind of what you would expect, because you'll always have in the system. So we'll just kind of bend over like this. Probably clean. Yeah, 100%. Goodie. So let's do one more liquid well, and then we do one gas well, and then it's a recess or summer vacation, or I guess it's fall break now, but whatever it is. So we're going to go to the Crow well. And we're going to click PVT. And we're going to just add, here just click save on the PVT. We'll assume that SP did a great job there. Hopefully they did. We are going to assume that the production data and the bottom hole pressure data is perfect for us. That'll be good. And then we're going to go to flow material balance. And we're going to run it. Here we don't have as much data. We see we have a little buildup. I'm going to try to honor that. And we see we have this nice early time portion of the data that I'm going to go ahead and try to fit and zoom into right here. So I can just take that data, either lasso fit it or whatnot, maybe something like this. Get 1.9, and I just rerun the model. I'll show all those steps one more time. Just go ahead and pick your Crow well. Launch the PVT. Go and click the flow material balance. Click run. And get this early time portion of the data. That yields a pretty good agreement, but we have this buildup here. And if we assume that that buildup was a real buildup, we've learned today that we are allowed to make this pore volume slightly lower. And then when you do that and rerun, hopefully we'll be able to say that we're above. Maybe we'll just ignore those few points. And I'll make everybody make their own interpretation here. And we're going to go over to the recovery factor analysis. That's the last thing here. Okay, so if we go to recovery factor, maybe I'm too fast. I'm just going to give everybody 20 seconds here. There we go. So once we're happy with that, we have our contacted pore volume. Mine is at least 2.2. Maybe if I want to honor that buildup, if we think that's a real buildup, I can maybe be even more generous. So let's, you know, can even take it further down. That's only if we think it's a solid buildup, but we trust the data, of course. And then that would be by definition my lowest estimate of the contacted pore volume. So when you have that in place, you go to your recovery factor analysis. You go ahead and add these points. The same goes here. Just make sure that your data points has a positive type of intercept right here. Once you're happy with that, you simply click run. And then you get a set of EURs. You can double. It looks decent here, I think. The QMGUR in the forecast. And I can also make, you know, in practice, I would probably run the DCA first, honestly, but a DCA forecast for this guy is at least 532 MSDB. And my recovery factor gave me 500 for this guy. Goody. Is that easy enough, or was it too fast? It's most likely too fast, and then I apologize. But if it was okay, let me know. Yeah, the PHP forecast assumption here to the right, there's a few things that you can set. You can set the forecast start date. By default, it's the final date. You can change this number to whatever you want. So I can make this, for instance, 1300, and that will move this point up and down for where it starts from. You can change this to 500, the final abandonment pressure. And then you can also change the nominal decline rate here to something either less or more aggressive. And then once you've done that and recalculate, I lower the abandonment pressure. That will increase my EURs and my recovery factors by a little bit. Maybe I get that additional percent that I'm looking for. Yeah, a couple of percent. And I lowered the abandonment pressure by 200 psi. Awesome. Tizon?
Oh, sorry.
Yeah.
I accidentally touched my mic.
No worries. Okay. Okay, we're going to do one last thing. We're going to do this for a dry gas well. And this is just to kind of get it in your fingers. For a dry gas well, I'm going to do the 37 well, which is the fastened well. We go to PBT, reservoir fluid composition, change the method from GOR to one suggestion is just expose the GOR plot as defined. That's probably a great suggestion, Hari. Just so I understand it correctly, when you say expose the plot there, are you talking about
the GOR versus the oil?
Yeah, okay, like actually show it. Yeah, I see what you mean.
As you're plotting, because you can clearly see sometimes the GOR as a slight shift up, and it's kind of a art versus a science there. So you can clearly see that.
That's a good point. I'm gonna actually suggest, because the flow material balance plot down to the right, it's kind of like, I don't know, it doesn't have a function. So maybe we can actually change that with the flip.
Yeah, I think so.
Yeah, it's actually a good suggestion. I'm gonna bring that up to the guys. Good suggestion. GOR versus Q.
Or at least enable a smoother trend from current production more granular trend in the next 6 months to 1 year to 2 years out of it, rather than us defining the points, because that can come up with a very different set of results.
Yeah, exactly. So I mentioned that for the previous group, that a couple of things that probably will come into the software on this front is the toggle that I talked about to kind of invert the axes. It's an auto fit for those buttons, such that you have it there when it comes to like the CGR versus pressure. And also an auto fit of the multiphase FMB. Now, the reason why the auto fit of multiphase FMB needs a little bit more logic, right? Than, we have the auto fit in, analytical RTA, and that's like pretty, now it changed to well, but it's pretty straightforward. It's just trying to fit a half slope while the PNR plot is giving you a, or a half slope on the PNR plot. Just fit that period of data, like what you see here. But it's not as trivial for the multiphase, because you need to know, are you saturated, undersaturated, all the things we talked about. But that's also on the drawing board. So I just wanted to mention that. But
I think FMB is quite intuitive the way you've designed it now. The instant OGR fit may be sped up a bit with the auto fit and exposing the GOR versus oil trends.
Yeah, I agree. That'll be awesome. So I promise we'll be there this year. Let's see that.
Got it.
I need to watch what I'm promising. It bites me in the butt sometimes, but I'll make sure the next release everybody's going to be amazed. It's going to be good. So the last thing we're going to have to do, we're going to do the pheasant well in PVT for pheasant. Change from the GOR method to the dry and wet gas and just make it 0.6. That's how it is for these type of fluids. So when you have 0.6 there, and we have production data, bottom pressure data, we're ready to do our multiphase FMB or our FMB. So, and one thing, here, the phase envelope is basically empty. And that's because it's so dry, there's no two-phase region. So that's totally fine, nothing to worry about. And then once we're done with that, we're ready to do the flow material balance. By default now, the flow material balance is picked to be gas. So in that case, we're starting with the arguable material balance, and you can probably, through a couple of iterations, you'll see that it's an iterative method. Maybe that was a lucky strike from me. At around 2.2, maybe as an STB. Everything, all the principles apply. Check the pressures. It's a little bit iterative, so you see the updates every time you draw the slope. Totally fine. So this was around 2.3 BCF, and you can do this exact same thing with the multiphase FMB. And for Kimberly, it's a very good question there. How would it look like for you? Well, it will look exactly kind of like you're going straight into the second period here, and your pore volume will be this guy, and we see this is around 23 BCF right there. Yeah, and that's been also requested the lasso fit for the other method there. My point for you guys is that the OGIP from both methods should yield very, very similar results, around 23 BCF in both of these cases. Very good. Since I have a little bit of time, I'm just going to show real quick the thing that T-Swan was mentioning. I'm just going to create a synthetic oil well, make it multiphase, all that stuff. Going to make it, and of course, if we're going to use the multiphase FMB method, we need to make sure that it goes into some kind of boundary at some point in time here. I'm going to launch this data. I'm going to launch numerical RTA here. I'll just take this flow material balance. If I run it, See the slope for material balance in this example, spot on both early time and late time actually. You'll see that for those of you that are interested in that. This line, before and after you go below saturation pressure, the lines are and then in our model for numerical RTA, we get this. It's like around 700,000. It's going to be a little lazy here. I'll pick that pore volume, and you see we're between these two stems right here. I should probably have added some more stems. So 3.2, and we are at 3.6, and it's below 5. So that's basically between those two. So there's no reason why they should be kind of inconsistent if you are in full boundary. But obviously, what you run into in practice is numerical models, numerical RTA uses rel perms to all these ratios come from that. While in the flow material balance, you've been using these empirical ratios in the future that you forecasted yourself. So that's kind of the thing you run into.
Okay, so meaning to say, Matthias, if I'm interested to know how much, when I create a frag, how much OIP has been contacted, I can use NRTA methodology, or I can use fluid material balance. And if I were to both, they should be reasonably matched. But with the exception, in the numerical simulation, you kind of doesn't allow any recovery beyond the fracture tips.
Yeah, skip the last part. Everything else in the last part was correct. So your flow material balance and the RTA exercise can give you an estimate of the contacted pore volume, both of them, if you're in full boundary. The difference is that your flow material balance, there will be a delta between the actual size of the tank and the flow material balance if you're still infinite acting or in transitional. And the similar thing with the numerical RTA will just be able to provide you the lower estimate, right? So what will happen if all the type curves are infinite acting, and a lot of you guys have seen that on this plot right here, all the different stems are basically overlapping, the data is overlapping, that's just a definition of something being infinite acting.
Okay, so I want to understand the concepts on the fluid material balance because let's say after producing for 3 years, your pressure has dropped, let's say from 5,000 to 3,000 pounds. And then based on your SO and SW panel, you actually can kind of calculate during that time in my SRV, how much is our saturation, likewise, what is the SW, what is SG, approximately. I think I asked this question, there's a reason for that is, okay, we can discuss at a different occasion, and so you can, right, if you want to.
Yeah, that's what it spits out.
This is a tank model, I have to say.
Yeah, it's a tank model. So like while I think you alluded to it, like any type of RTA exercise, they assume some kind of geometry, and that's just an assumption when you do RTA. You don't, and it's the same when you run a simulation model or a complex model or a simple model. You assume some kind of geometry, and that's the world that you're doing. You're enforcing that on it. Flow material balance, if the thing behaves like a tank, it doesn't care about how that's shaped. So that's kind of one of the differences between the two. And the room for inconsistency is if you're not in full boundary dominant.
Looking for food?
Awesome. That was my dog here, so probably good time to stop the course. Thank you everybody for on Kimberly's question. I'll get back to you. I'm gonna double check that actually. No, I think you're right. I'm gonna check that real quick and see how it looks like.